Hey everyone, I'm asmollizard, and today you get to delve into my mind as I try to solve this PnC question from TJC's 2016 mid-years paper. Basically, we have this John has 5 shirts and 3 pairs of pants, each of different design. And as a normal human being, he's gonna wear 1 shirt and 1 pants every day from Monday to Friday for the first week. And of course, equal probability and all that, and part I and part 2 are right there. So do try out this question if you haven't, and I'll see you guys in about 3 seconds. Alright, here's how I would do it. So first thing to take note, what I like to do, underline my information. He has 5 shirts and 3 pairs of pants. He wears it for Monday to Friday, which is, well, I live long enough, so it's 5 days, alright. So part I, John will wear a different combination each day during his first week of work. So because we're looking at different combinations, the keyword combination, so it's good to find how many different possible combinations he can wear. And it's quite simple. Right, 5 times 3. Alright, every shirt you can wear with 3 different types of pants. So you have 5 of shirts, therefore 5 times 3. Alternatively, you have 3 pairs of pants. Each pair of pants can be worn with 5 different shirts. So 3 times 5, right? Both will be the same 15. Okay, so because you wear a different combination each day, well, on the first day, he has 15 combinations to wear. Tuesday, 14, Wednesday, Thursday, Friday, 13, 12, 11. Alright, so simply put, the probability, so what I like to do is required probability simply equals to, first day doesn't matter, right? Because 15 out of 15 is just 1, and honestly, whatever happens, he'll wear something. Alright, so I can easily leave out 15. So I know that I'm going to do 14 over 15 times 13 over 15 times 12 over 15 times 11 over 15. Alright, so there's still 15 combinations that he can wear every day, right? Because, well, he can always wear the same set of shirts and pants on the next day. So it's still 15, still total 15 cases, alright? There's no such thing as no replacement here. There is replacement, quote-unquote replacement down here. So my calculator is quite simple. 14 times 12 times 11 divided by, you times 15 4 times. So 15 power 4, and you'll give you this, well, a bit of a anxiety-inducing fraction. And if you want to leave it in 3 different figures, 0.475. Alright, this is actually, don't use blue, let me use red, black. So this is actually 0.47454811481. Alright, and this is the answer for part I. Okay, now part 2. John will wear his favorite pants for the entire week, given that he'll wear a different combination each day. So clearly this is a conditional probability because you have the words given that he'll wear a different combination each day, which means that we'll be using the formula for conditional probability where we have PA given B equals to, well, both of the events occurring over PB. Of course, it should be quite logical, right? If this has already happened, find the probability that this will happen if this has already happened, which means that both events will have occurred. Therefore, PA times PB, or rather, PA intersect B. And then you divide by the probability that, well, if the event has already occurred. Okay, so we're going to use that idea here, but of course, we can't just write this down because we haven't defined A nor B yet. So instead, we don't define anything, just straight away write this fraction down, but substitute with the relevant probabilities. First idea is, how do you find PA intersect B? Which is, he wears his favorite pants each day and he wears different combination each day. So if he wears the same pair of pants, then, you know, he must have basically worn 5 different shirts each day. Right? So because if you have the same pants each day, then the only way to change your combination is with the shirts. And because you have 5 different days, all 5 shirts will be worn. So if you look at the pair of pants and shirts individually, well, essentially, to wear the same pair of pants every day, you have 1/3, and then 1/3, 1/3, 1/3, 1/3. To wear a different shirt every day, first day you can wear any shirt you want, so it's 5 out of 5. Next shirt, 4 out of 5, then you get 3 out of 5, 2 out of 5, 1 out of 5. Alright, so that is the whole idea behind part 2. So very simply, this is quite simple. You know that PA intersect B is simply 1/3 the sum of all these two numbers, where the top multiplies the bottom. So we have 1/3 times 5/5. Now, is it plus or minus? It is times. Sorry, is it plus or multiplication? It is times. Alright. Because Monday multiplied by Tuesday, because you're looking at all 5 days in a row. If you add, it means that you're combining the probabilities for one particular event. In this case, you have 5 each day that are all dependent on the previous day. So 1/3 5/5 times 1/3 4/5. In fact, you can just not use times, you can just continue use 1/3 3/5, 1/3 2/5, 1/3 1/5. Alright, then bottom basically PB, the probability of him wearing a different combination, which is simply the previous answer, 8008 over 16875. Now in your calculator, well, because since you've already calculated the denominator in the previous part, you can use the ans function on top. Now basically you're multiplying 1/3 3 times, so 1/3 power 5. Then you're multiplying 5/5 4/5 3/5 2/5 1/5, which is simply 1 plus 0.8, 1 times 1, 0.8, 0.6, 0.4, 0.2. So 1 times 0.8 times 0.6 times 0.4 times 0.2. Okay, below simply ans. Then you'll get back a very nice fraction. When I mean nines, numerator is nice, 13003. Alright, and that is the answer to part 2. Alright, so either you use the given probability, which is the universal method, or what I like to do is actually what I call by zooming. Okay, so back to part 2. Given that he'll wear a different combination each day and wear his favorite pants for the entire week. So when I deal with conditional probability, if I don't want to really think that much, or if it's not that obvious, I will then use the formula. But what I really like to apply is what I call by zooming, which is basically, since he's going to wear a different combination each day and he'll wear his favorite pants, so how do I combine both of them? Alright, so essentially what I'm going to do is, alright, out of these different combinations, how many ways can he have these different combinations, right? So you have 15 different combinations. You're gonna need 5 of them, right? So total number of different combinations is 15, choose 5, which is 3003. Alright, so there are 3003 ways to wear 5 different outfits, 5 different combinations in the week, in his work days. What is the number of ways for him to wear his favorite pants for the entire week and still have different combinations, right? So as we've seen, he's gonna wear the same set of pants every day for 5 days. The only thing that will make and ensure that he wears a different combination each day is the shirts. And he has 5 shirts only. So it will be shirt 1, shirt 2, shirt 3, shirt 4, shirt 5. You notice that there's only one way. Because he only has 5 shirts, he has to essentially allocate differently 5 of them, and which is all of them, right? So there's only one way for him to wear the same pants and still be able to wear different combinations. All right, so therefore the answer is simply 1/3003. There is one way out of the 3003 ways for him to wear the same pants and still maintain the idea of wearing different combinations every day. So this is what I mean by zooming, when you eliminate the other factors and only focus on the condition that has already occurred, which in this case, since he's going to wear different combinations each day, well, that will be my environment, that will be my circumstance that I'm going to look into. So instead of just considering the entire population, I only zoom in on the condition that's already satisfied, which is zooming onto the fact that he's going to wear a different combination each day, and then find the probability from that. Alright, I'll give you more examples on the idea of zooming in the next video, and this is how I would do this question with my lizard brain.